All right, welcome ladies and gentlemen. This is our video on the effects of IMFs in liquids. In this video, you're going to be learning about how the strength of intermolecular forces of attraction affects surface tension, capillary action, viscosity, vapor pressure, and boiling point. The big emphasis, the ones that we really need to know, are vapor pressure and boiling point. Those are really the ones that come up most frequently and that we see the most questions on, and that really sort of affect liquids on a day-to-day basis. So first up is surface tension. Surface tension, which you're probably familiar with, I know you've observed this in real life multiple times, is sometimes colloquially referred to as the skin on a liquid surface. And essentially, the reason that we see this sort of a skin or a layer on the top of a liquid is because the surface molecules are only attracted inwards. This is compared to the rest of the other molecules in a beaker or a pond or basically any sort of sample of liquid. The molecules that are in the middle, right here, they're attracted in all directions, so they're pulled in every direction in 3D space because they have IMFs with all of the liquid molecules that are surrounding them. But the liquid molecules that are on the surface of the liquid, they're only attracted inwards. There's no liquid molecules in the air up here, so there's going to be nothing pulling the liquid up. It's only being pulled down and to the side. This means that the surface molecules are packed significantly more closely than the molecules that are in the center of the liquid, that there is actually a stronger attraction between them because they're not being pulled in all directions. They're essentially being pulled in essentially two directions instead of all three. And that leads to what we call surface tension. And surface tension, by definition, is the energy required to increase the surface area of the liquid. So you can think of this like the energy required to essentially pull apart the molecules that are on the surface of the liquid. How much energy is needed to sort of separate them a little bit more? And based on this definition, energy required to separate, to increase the surface area of the liquid, so energy required to separate the liquid molecules that are on the surface of a liquid, if you have stronger intermolecular forces of attraction, more energy is going to be needed to do that. So therefore, surface tension is going to be greater. So what we see, the big point, is that we have significantly stronger, higher surface tension for compounds that exhibit stronger intermolecular forces of attraction, which should make sense, right? The more these molecules are attracted to one another, the more you're going to have to put in energy in order to separate them. The more of a skin you're going to see, the more of a sort of a layer on the top level, top of a sample of a liquid you're going to see, and that's our surface tension. Cohesion and adhesion. Cohesion is the attraction between like molecules, and adhesion is attraction between unlike molecules. So cohesion, basically, it has to do with attraction for both of them, but with cohesion, it has to be the same molecule that's attracting. So this would be, for example, water to water. Adhesion is attraction between two unlike molecules. So an example of this might be sugar and water. There's an attraction in both of these cases. Water is certainly attracted to itself. We call that cohesion. Sugar is also attracted to water. They both exhibit hydrogen bonding, but we call that adhesion in that case. Now, a classic example of where we see cohesion versus adhesion, this sort of example of attraction between compounds that are the same versus attraction between compounds that are different, is by putting different liquids in a glass tube. So in this one, we actually have mercury. And in this one we have water. And what you see here is that the meniscus, if you look at the meniscus of the mercury, it's actually an upside down meniscus, quote unquote upside down, based on what we're used to seeing, versus the meniscus for the water, which is absolutely what we're used to seeing. And the reason is what's going on where the liquid hits the glass. So this is a conversation about adhesion, actually. How much, in this case, is the mercury attracted to the glass that's on the side of the container versus how much is the water attracted to the side of the container? And you see here that there's very little adhesion. The mercury is not attracted to the glass. So there's very, very little adhesion there, which actually causes this quote-unquote upside-down meniscus. It's not attracted to it. Versus here with the water, now there is a lot more adhesion. and the water molecules have sort of risen up the side of the container because they're very much attracted to the side of the container. Now this then causes what we call capillary action, where liquids can spontaneously rise in a narrow tube, seemingly defying gravity, right? Water will go up a narrow tube even though gravity is pulling it down. This is based on adhesion. This is an adhesive property. However strongly that liquid is attracted to the substance that's in the tube, if it's attracted very, very much, then it's going to adhere to it, it's going to rise up, and that's capillary action. Tree roots work by capillary action to pull in water, and we see the stronger the adhesive intermolecular forces that we get, the more capillary action we'll get. Basically, the more that these two compounds are attracted to one another, the stronger their attraction, the more capillary action, the higher up the liquid can rise. Viscosity. I don't know why it's going through. There we go. Viscosity is, by definition, the measure of a liquid's resistance to flow. And I really like to think of this one right here. This is our definition of viscosity, resistance to flow. How much a liquid resists flow. So if it resists flow very, very much, then we call that being highly viscous. If it doesn't resist flow much, then it's not viscous, it's less viscous. So molasses, for example, would be a highly viscous liquid. It resists flow a lot because it's very sticky and very gooey. Water is significantly less viscous than molasses. So that's what that term means. Now, as you might expect, if you have something that has very, very large intermolecular forces of attraction, that means that your liquid molecules are going to be very attracted to one another. That will cause them to resist flow. So that increases the viscosity. Or molecular complexity, meaning the larger the compounds get. So what we have here, we have C4H10, which is relatively small, and it's not very complex. So there's not, it's not very viscous. It doesn't resist flow. There's less intermolecular forces of attraction. But like we've talked about with London dispersion forces, the larger your molecule gets, the more London dispersion forces you have because you have more electrons. Also, the longer, remember, surface area, right? This is a very long molecule, so it's going to be very, very viscous because you see we have this whole big thing right here, right? We'd say this is a more complex molecule, so it can form a lot more intermolecular forces of attraction with this sucker that's right next to it, and that's going to make it a more viscous compound. Vapor pressure. This is a fabulous name. Vapor pressure is a great name because by definition it is the pressure of a vapor over its liquid. But just to be very, very clear about this, vapor pressure is not the pressure of any gas over its liquid. It's simply the pressure of the evaporated liquid over the stuff that's still liquid. So if this is water right here, this is also water. So if we see how these particular water molecules are exerting a pressure, that's vapor pressure. Now, thinking about this in terms of intermolecular forces of attraction, in order to exhibit vapor pressure, your molecule has to escape the liquid phase, right? It has to, because that's where you get the vapor pressure from. It's not just any gas that's over a liquid, it is the evaporated liquid over the liquid that exerts the vapor pressure. So this basically saying that, hey, the more vapor you have, the more vapor pressure you're going to get, right? The more evaporated liquid you have, the more vapor there's going to be pushing down on the surface of the liquid. Well, how do you get more vapor? You get more vapor by having more evaporated liquid molecules. Well, in terms of IMFs, how do you get more evaporated liquid molecules? You get more evaporated liquid molecules if you have weak intermolecular forces of attraction. If you have very, very strong intermolecular forces of attraction, you actually have very, very low vapor pressure because it means that you're not getting your liquid evaporating. If your liquid molecules are highly attracted to one another, then they are not going to evaporate easily. And if they don't evaporate easily, you don't have a lot of vapor. And if you don't have a lot of vapor, you have very low vapor pressure. So that's a huge point about vapor pressure, that we actually see this sort of slightly inverse relationship with intermolecular forces of attraction. Now, something also to bear in mind with vapor pressure is that we are talking about a system that is at equilibrium here. So basically, in this example that we see with the picture, we simply stoppered the bottle, and we allowed the system to get to equilibrium. So I wouldn't really be talking about vapor pressure in this first sample because it's not at equilibrium yet. But in the second one, where I have no net change, right, where basically the amount of a liquid that's evaporating is equal to the amount of liquid that is condensing, the two systems are balancing one another out. Now I can start to talk about the vapor pressure of this particular system. If it was open, then your liquid would just keep evaporating because your closed system is now actually incredibly large. It would be sort of the size of the building or the size of the room. The we call liquids that have very high vapor pressure, we call them volatile. And that's what the word volatile actually means. This is a word that gets misused quite frequently. But volatile really just means that your liquid evaporates easily. And that it evaporates easily because it has very high vapor pressure. Your liquid evaporates easily because it has very weak intermolecular forces of attraction. So with vapor pressure, the huge key thing to remember is if you have very strong intermolecular forces of attraction, you have a very low vapor pressure. The system has a very low vapor pressure because your liquid isn't evaporating. And if it's not evaporating, then it's not generating vapor pressure. If your IMFs are very weak, then you're going to have a very high vapor pressure. Vapor pressure increases because if you have weak intermolecular forces of attraction, there's not that much of attraction keeping the liquid molecules in the liquid phase. They will go and they will evaporate. And if they've evaporated, then they can generate vapor and generate vapor pressure over the liquid. So larger molecules with stronger London dispersion forces, so we're looking at number of electrons, will have weaker vapor pressures or less vapor pressures. And more polar molecules, the more polar your molecule is going to get, i.e. if you have dipole-dipole forces or hydrogen bonding, then you have stronger intermolecular forces of attraction, so you're going to have weaker vapor pressures. Now, the effect of vapor pressure with temperature. Temperature is the only thing that impacts vapor pressure, that along with the strength of intermolecular forces of attraction. But I mean, if you have a compound and it has the IMFs that it has, temperature is the only thing that's going to change vapor pressure, and it has to actually do with Maxwell-Boltzmann curves, because we're used to seeing this curve. So if this is at a low temperature, and this is at a high temperature, and hopefully you feel fairly comfortable with how this curve has shifted from the low temp to the high temp, that we've sort of shifted it to the right and flattened it out. Well, this is the temperature, energy needed to overcome intermolecular forces in your liquid, right? That's the temp at which your liquid can evaporate and generate vapor and generate vapor pressure. If you increase the temperature by shifting the distribution of molecules, well, now this energy has stayed the same, but now you have more molecules that have the sufficient energy to escape the vapor, to escape the liquid phase, become a vapor, and generate vapor pressure. So at higher temps, greater number of molecules here have the necessary energy to leave the liquid phase, break their intermolecular forces of attraction, become a vapor, create more vapor, generate more vapor pressure. Temperature is the only thing, that is it, the only thing that impacts vapor pressure. You're going to see some trick questions tomorrow about that, so just be very mindful about that, that the identity of the liquid and the intermolecular forces it has, along with the temperature at which it is, those are the only things that influence vapor pressure. So looking at this is a vapor pressure curve. Now you might remember you had a reference table that had a graph like this in Regents Chem. You obviously don't have one now, but you might be shown one on a test and simply asked to read it. So this is just showing three different compounds, diethyl ether, ethanol, and water, and it's showing their different vapor pressures. And you'll notice that in the case of all of them, as your temp is increasing, so as temperature goes up, for all of them, their vapor pressure is increasing. That's simply showing that more liquid is evaporating and then generating vapor pressure at a higher temperature. You'll also notice that of these three, water has the lowest vapor pressure. of the three at any given temperature, right? If I picked like, 30 degrees Celsius and I looked at the vapor pressures, these are the three vapor pressures. Water is the lowest. It's the lowest consistently. That means that water of these three compounds has the strongest intermolecular forces of attraction. Right, weaker vapor pressure, less vapor, because they're sticking together. The compounds, the molecules are sticking together very, very strongly. Boiling point. Okay, so I'm a goober, and I actually find it absolutely fascinating that the definition of boiling point is not like the point at which something boils, because that's actually as counterintuitive as you think that is. It's actually not the definition of boiling point, and I'm very much intrigued that this is the definition of boiling point. It's the temperature at which the vapor pressure of your liquid is equal to the external atmospheric pressure. Boiling occurs at whatever temperature that is. Whatever temperature where your vapor pressure is equal to your external atmospheric pressure. That is boiling point. And I actually love this definition. I think this is a fascinating definition of boiling point, because we're so used to it's just the temperature at which it boils. Yes, but what's causing it to boil? And you'll notice there is this enormous relationship between vapor pressure and boiling. That boiling is actually defined in terms of vapor pressure. It's basically saying, hey, look, your liquid will boil whenever its vapor pressure is equal to the external atmospheric pressure. In essence, what's happening is it's the pressure at which the atmosphere can no longer contain the vapor, because once they're equal, then your vapor, then basically everything's going to separate. Now, instead of just having a few compounds separate, now everything is separate. Your atmosphere can no longer contain the liquid. This also means that your boiling point changes at different pressures. That's what this is saying, that the boiling point of water here where we are is not the same as the boiling point of water in Denver, where you're a mile high up and your atmospheric pressure is significantly less. Yes, it's less, not more. It's less. Think about that. So we do like to standardize things, though, in science. So we've called normal, quote unquote normal, 1 atmosphere. So this term normal boiling point means the boiling point at 1 atmosphere, external pressure. Therefore, the vapor pressure at your normal boiling point is also 1 atmosphere, because the definition of boiling point is when vapor pressure equals external pressure. So when we refer to normal boiling point, we mean the boiling point at 1 atmosphere. And the normal boiling point of water is 100 degrees Celsius. We know that. That's the temperature at which water has a vapor pressure of 1 atmosphere. Now, in terms of explaining boiling point in terms of strength of IMFs, well, I'm going to explain this in terms of actually the different liquid properties that we've talked about in this video. If a compound has extremely strong intermolecular forces of attraction, that means that it's going to exhibit a very high surface tension, and it's going to take a lot of energy to pull the surface molecules apart because they're very highly attracted to one another. Well, if it has a very high surface tension, that's going to make it difficult for your particles to escape, for your molecules to escape, to break their intermolecular forces of attraction. That's going to lead to not a lot of vapor, to very little vapor. It's going to also mean that your particles have to be moving very, very fast, and they have to have a lot of energy. They have to have a tremendous amount of energy in order to escape the surface tension of the liquid. So it's going to mean that your particles have to be at an extraordinarily high temperature to escape your surface tension. So your molecules have to be at a very high energy in order to have enough particles that have sufficient energy to escape the liquid, become a vapor, and generate enough of a vapor pressure so that it's equal to the atmospheric pressure, which means that this compound is going to have a very high boiling point. I know that's kind of a lot, but notice how this is all sort of pulled in together, right? High surface tension and low vapor pressure combine to basically say that, hey, this structure is going to have a very, very high boiling point because of its very, very high intermolecular forces of attraction. So that is the discussion on effects of intermolecular forces of attraction, and be prepared to answer questions about this tomorrow.